All right. Hi, everyone. Thank you for being here. This is joint work with Arjun, Narayan, and Andreas Haeberlen from the University of Pennsylvania, and with Ariel Feldman from the University of Chicago. So, all of us should be familiar with how research papers are published. Initially, someone owns an interesting database. For example, the Eurosys organizers could have data about alcohol consumption during the banquet dinner. Then researchers like us can get this data set, issue multiple queries, and decide to publish some of the results in an interesting paper that we can all get to read. But sometimes these papers can have surprising results, like this one, that only 2.5 bottles of wine were consumed. Then the readers have every reason to ask for some kind of verification that the results were correct. The way that this is currently done is that the readers can get the database themselves, recompute the statistics, and check whether the numbers match. And unfortunately, mistakes in research do happen, and when they do, they make big, embarrassing headlines like this one, in which a paper published by two prominent economists was recently found to contain serious calculation errors. So we can see that verifiability is very important for scientific research. But what happens when this database contains sensitive information? For example, a hospital might have a data set that contains medical information. The first challenge with such a data set is that the result itself that's being published in the paper might leak information about individuals in the database. Several cases in the literature have shown that sensitive information can be disclosed through aggregate results or even through anonymized data sets. The second challenge that we have is that the study cannot be verified. And this happens because the data set is sensitive, so most readers won't have access to it. And since they don't have the data set, they cannot recompute the statistics and be convinced that the study is correct. So these two challenges are conflicting with each other because, as you can see, the first challenge requires hiding information, whereas the second challenge requires revealing information. So it's natural to ask, can we ever have both privacy and verifiability? And one possible approach to get privacy guarantees is to use differential privacy. Differential privacy prevents the published result from leaking a large amount of information. This is achieved by adding a carefully chosen amount of random noise to the result. We are not going to talk about how this noise is chosen, but the result is that this noising provides strong mathematical privacy guarantees. Unfortunately, differential privacy makes verifiability even harder. And to understand that, consider the following example. Suppose that the researcher's hypothesis requires a specific value that would make their hypothesis valid. For example, the 2.5 bottles of wine that we saw before. Then what prevents the researcher for publishing a paper containing that number? Then, even if the readers had access to the database, and most readers won't because it contains sensitive data, they could compute the statistics again, find that there is a difference, and the researcher would still have plausible deniability. So we can see that differential privacy by itself makes verifiability even harder. A more sophisticated attempt is to combine differential privacy with zero-knowledge proofs. Such a solution would work like this. First, we would need someone else to create the noise so that the researcher cannot pick a convenient noise. For example, the data owner could do it, or the subjects that participated in the study that is contained in the database. Then the researcher would go ahead and publish a noised result, but using that noise, which is chosen in a safe way. The second thing that the researcher can do is that it can use a tool, a system like Pantry, to produce a zero-knowledge proof. And then the readers could get the proof and check that the computation contained in the paper is correct. And this almost works because we get verifiability. But the problem is that this approach creates a subtle privacy challenge. And this happens because if we naively generate the proof by tracing the execution of the query, then if that execution depends on the data of the database, one could look at the proof and infer information about individuals in the database. We call this problem structural privacy, and in what follows, we will see how we dealt with this problem. So this brings us to our approach, which is to build a new data analytics tool that produces verifiable results and provides strong privacy guarantees. And we call our system VerDP. And with VerDP, researchers can publish results that are differentially private. They can publish zero-knowledge proofs that are computed efficiently. And moreover, our compiler will make sure that the result of the paper is differentially private and that the proofs are structurally private. So with VerDP, we can have both. We can have both privacy and verifiability, the two goals of our paper. So far, I've described the motivation and the basic approach of VerDP. In what follows, I'm going to talk about how VerDP achieves its goals. So one particular challenge with differential privacy is that it is hard to know whether a given query is differentially private. This is true because proving that the guarantees hold requires expertise that most researchers don't have. Fortunately, people working on differential privacy have managed to build compilers that automatically certify whether a query is differentially private. As a result, even non-expert researchers are able to write privacy-preserving queries. We can definitely use one of these languages to get differential privacy guarantees. But can we do the same for structural privacy? Ideally, we would like our compiler to make sure that our compiled queries satisfy both differential privacy and structural privacy. So we begin building our system around Fuzz, which is one of the languages that already provides differential privacy. And to understand why Fuzz does not satisfy structural privacy, let's look at this example. This is a query that counts how many people are older than 40 years old in a database. This is the predicate that returns true if a person's age is more than 40 years old, and this is the query itself. This query first applies the predicate to the database, and after that, it splits the database into two intermediate databases based on the age of the people. Then, this query counts the number of people being over 40 years old, and finally, it adds a random amount of noise to provide differential privacy guarantees. Hence, the final result has been noised and is safe to publish. But the rest of the execution was not designed to preserve privacy. And suppose we trace the execution of this query to construct a zero-knowledge proof for this query, then the size of the intermediate databases is reflected in the structure of the proof. So even if the proof is zero-knowledge and generally hides the actual values of the execution, a reader could look at this proof and understand the execution trace and infer information about the dataset. For example, in this proof, the reader could understand that the exact count before noising is 3. And this is only one instance where the structure of the proof can leak information. There are other data-dependent language primitives that could violate structural privacy. So to guarantee that there are no leaks through the proofs, we carefully examined Fuzz and found all the language primitives that are sources of structural violations, structural privacy violations. We either fixed or restrict those primitives, and the resulting language is called VFuzz. And what's good about VFuzz is that we were able to formally prove that zero-knowledge proofs generated for successfully compiled VFuzz queries always satisfy structural privacy. Due to lack of time, I'm only going to describe how we fixed the language primitive that splits a database in two. For the rest of them, you can always refer to the paper. So let's go back to the example of counting how many people are over 40 years old. To fix the issue, we inflated all intermediate results to the size of the original database. This way, the structure and size of the proof was not affected by the particular data in the sensitive dataset. Other language primitives required more complex fixes, and you can find more details in the paper. So far, we have talked about structural privacy. Now it's time to talk about efficiency. What is the cost of verifiability, and how much do we have to pay to generate these zero-knowledge proofs for large databases? As it turns out, the cost of proof generation depends on the size of the input. So large databases require very expensive proofs, even for simple queries. As we will see, VFuzz queries have a special form that helps us efficiently generate zero-knowledge proofs using Pantry. Before I explain how we leverage this form to efficiently generate proofs, let me tell you a few words about the costs associated with zero-knowledge proofs. Given a program, first we have a high setup cost, which is for compiling a query and creating the necessary cryptographic keys to generate the proof. Then, generating the proof is also very expensive. Lastly, we have the verification cost, which is pretty small compared to the first two, so it won't bother us. So in the following, I'm going to explain VerDP's design and how we were able to keep the first two costs affordable. So consider this large database and the query that counts the number of people older than 40 years old. As we described earlier, the proof will be too big to generate on a single machine. Our approach is to carefully split the proof into smaller pieces we call tiles. This is possible because VFuzz queries have a special form. For instance, in this proof, there is a part that applies the predicate on every single database entry, a part that counts the number of satisfying entries, and a part that adds the noise. Moreover, as we can see here, the computation of the predicate is symmetric because it applies the same function on every database entry. So we can further split the proofs such that the tiles that we have produce a proof for only a small portion of the database. By doing this, we get two great benefits. First, our tiles are reusable. And as you can see here, we needed to compile only 3 small tiles, and then we used those 3 tiles to generate the proof for the entire database. Second, by having many tiles, small tiles, we can parallelize them and use multiple machines to speed up the generation process. So we can see that by using tiles, VerDP is able to construct very large proofs quite efficiently. Of course, decomposing to small proofs into tiles is not straightforward. This is because we cannot simply reveal the intermediate results to the verifier. That would leak information. So to hide intermediate results, we use cryptographic commitments. By passing commitments instead of plain values, the researchers are able to prove that the output of one tile is indeed the input to the next tile without having to reveal the actual value. This way, VerDP can assemble very large proofs without sacrificing privacy. So we described how VerDP works, and now it's time to look at our evaluation. In the paper, you can find the answers to all these questions, but in this talk, I'm only going to focus on the first 3. So for our evaluation, we implemented several queries from the differential privacy literature in VFuzz. And these range from simple counting queries to histograms and even clustering queries like k-means. What's important is that these are useful queries that can be used to produce meaningful scientific study results. Furthermore, in order to reap the benefits of parallelization, we used 32 machines on EC2. And our machines had GPU acceleration to speed up Pantry's proof generation. So researchers should be able to generate a proof in time for their publication. So it is crucial to know how long it takes to generate a proof. This is the required time for several queries and several datasets of varying size, from 8,000 entries to 62,000 entries. We can see that even the largest proof would take less than 5 hours to generate. And you have to keep in mind that the proof has to be generated only once. Next, we consider how fast proof verification is. It is important that verification is fast because we would like all the readers to have the ability to verify the results. So we measured the time to verify the proof of our queries. And we did that for the same range of datasets as in the previous slide. And here, even the largest proof took just 3.5 seconds to verify on a single machine. And of course, this is easily within the means of all readers, no matter what hardware they have. Lastly, finally, some researchers might want to work on very large databases. So it's natural to ask, can we use many machines to generate larger proofs? And since we didn't have 1,000 machines, we estimated the time that it would take to generate a proof for the counting query for a data set of 131,000 entries. As you can see, with enough machines, this data set can be handled within a few hours. And we did that the same for other much larger data sets and found that the trend is the same. With enough machines, you can always bring down the cost to a few hours. And we believe that as cloud computing becomes more ubiquitous, VerDP will be able to handle larger and larger databases. To summarize, the goal of this paper was to enable verifiability of studies on private datasets. Our approach involved combining differential privacy with zero-knowledge proofs, and the main challenges were to provide structural privacy and efficiently generate the proofs. Our evaluation suggests that VerDP's costs are affordable. So thank you, and I would be glad to answer your questions.
Questions? No questions? Can you give an idea of what the proofs look like?
What the proofs look like?
Mm-hmm.
It depends on the system that you use. For example, in Pantry, they are a set of constraints, and you prove that these constraints are satisfied, so the execution was correct. It's complex mathematics. But then the final proof that is sent to the readers is just 280 bytes, and it's a small cryptographic value that you can verify.
Okay, thank you. Other questions? Okay, thank you.